So in our last video, we talked about the structure and behavior of electrons and how that resulted in unique emission spectrums of atoms. In this video, we are going to kind of switch our focus to a different part of the atom, and that is the nucleus. Now, with our understanding of the nucleus of an atom, we can actually begin an introduction into nuclear physics, which is really just anything to do with an understanding the physics of the nucleus of atoms. So our objective today is to be able to describe nuclear stability and to calculate the mass energy equivalence of a particular scenario. And the essential question that you all should try to answer at the end of watching the video is, how does energy and force affect the stability of an atom's nucleus? So there's a lot of obscure topics in here, and there's quite a bit to cover related to nuclear physics, but I hope this video is going to give you a general overview of what nuclear physics is about. So the first thing I want to go over is, again, just a quick review about the atomic nucleus. So remember, atoms are made up of a nucleus and an electron cloud. Now, within the nucleus, we have two different types of particles. We've got protons and we've got neutrons. Again, we call these subatomic particles. But we also call protons and neutrons specifically, since they're in the nucleus of an atom, nucleons. So that's a new vocabulary term we can be using today. And nucleons, again, are just the protons and neutrons within the nucleus of an atom. And we talked about in one of our other videos how they are held together by the strong nuclear force, right? So thankfully, we have a very, very, very strong force, which we literally call the strong force, the strong nuclear force, holding the nucleons in our atoms together, to preventing them from breaking apart. Now, if, say, we wanted to break apart the nucleus of an atom in some particular way, we would need to input a certain amount of energy. Now, that energy is what we call the binding energy of the nucleus. Again, it's the amount of energy required to overcome that strong nuclear force and break apart a piece or the entire nucleus of an atom. So that's what we will be predominantly looking at today in this video. Now, again, when we talk about the structure of an atom, this is really well represented on the periodic table of elements. Again, I will always call that periodic table one of our best cheat sheets scientists have ever invented, because there is so much information on there for us. So again, within each box, we have the atomic number, which determines the number of protons we will be seeing in the nucleus of that atom. So to your left, I've drawn an example of a lithium atom. You can count it up. It has 3 protons, it has 3 neutrons, and it has 3 electrons, all right? So again, that atomic number indicates the number of protons in the atom, and it also identifies, or it determines the identity of the atom. Lithium is the only atom with 3 protons. Now, our atomic mass describes the average number of neutrons and protons, and I probably should add that to clarify, in one of those atoms. So again, we know that the number of protons is never going to change. If we were to have a different number of protons within an atom, it would be a totally different type of atom. But we can change the number of neutrons. And that is what kind of gives us these decimal numbers here for our atomic mass, because we are taking the average atomic mass of various different variations of the same type of atom. Now, these different variations of the same type of atom are what we call isotopes. So I will highlight that because this is going to be an important word. Again, isotopes just means that the atom is changing the number of neutrons within its nucleus. Again, you'll see for this example, there are still 3 protons in both of these atoms, which indicates they are both lithium atoms. These are both lithium atoms, but they are isotopes of one another, meaning that they actually have a different number of neutrons, which causes them to have a different atomic mass, because one is going to have a greater number of neutrons, causing it to have a larger atomic mass. Now, the last thing I will point out related to atomic mass is that it is measured in a universal mass unit, which we represent with the lowercase letter u. So when we're counting up the number of protons or the number of neutrons in an atom, we're actually measuring that mass in the unit, in the universal mass unit instead of kilograms. And the reason is because atoms are so small that it really doesn't make sense to have to deal with these big numbers if we're working with atoms all the time in nuclear physics. So just so you all understand, one universal mass unit is the same as 1.7 times 10 to the negative 27th kilograms. So that is just how small those protons and neutrons that we are working with in nuclear physics are. So now that we've established this concept of isotopes, I do want to talk about this idea of nuclear stability. And really what this is getting at is just understanding that while atoms can have different isotopes, they can vary in their number of neutrons, there are only specific variations of these atoms that are actually really stable and that they will actually exist in nature. And that is what we're getting at with nuclear stability. So as we, this is a very popular chart. If you were to Google, nuclear stability and radioactivity chart, you would see a chart that tends to look like this. So as we go across the periodic table and down the periodic table, atoms are going to be increasing their neutrons as well as their protons in their nucleus. So we start to see this upward trend. And these little blue dots, what these are representing are the stable isotopes, meaning the atoms that exist that have a particular number of protons and a particular number of neutrons, or that proton to neutron ratio is very, very stable. It likes to remain in that state. So, for example, lithium, seeing how it's 6.94, that's closer to actually an atomic mass of 7, meaning that it tends to favor this particular isotope up top here, instead of the isotope that includes 3 neutrons. It tends to favor the isotope that includes 4 neutrons. So that is going to be our what we call the more stable isotope. It's more readily found in nature. So again, other isotopes can exist with different amounts of neutrons, but our stable isotopes are going to be the ones that are most popular and most often found and naturally occurring. Now, these isotopes that are unstable, they still exist. This isotope with 3 protons and 3 neutrons of lithium still exists in nature. It just might not be as stable as a variation of lithium that has 3 protons and 4 neutrons. So these variations, these isotopes that still exist but aren't as stable as our other stable isotopes are what we call radioactive, meaning that, Again, they exist, but they like to change themselves to become more stable. And I will explain what that means, because there's a variety of ways that these atoms can change themselves and the makeup of their nucleus to become more stable. So if we have an atom, with a particular number of protons and neutrons, I'll just get my pen out. Say we have an atom down here, right? It's kind of actually, it's got its number of protons here, and it's got a number of neutrons. All right, so it's actually got a little, and that's a not very straight line, but it's actually got more neutrons than it really needs. So what it wants to do is actually find a way to get to a more stable version of that atom by getting rid of some neutrons there. So we'll talk about ways that atoms can kind of shed the number of neutrons or increase the number of neutrons within their nucleus to become more stable forms of that atom, more stable isotopes. All right, so one of the ways that atoms can kind of either shed those neutrons or increase the number of neutrons in their nucleus to become more stable is through what we call a process called nuclear decay. So I will highlight that. Oops, I'm using a pen instead of my highlighter. So again, nuclear decay. The ultimate goal of an atom undergoing nuclear decay is to achieve stability. And we have 3 different types of nuclear decay. The first type of nuclear decay we know of is alpha decay. And you'll see this weird symbol in parentheses next to the word alpha, and that is simply our Greek letter for alpha. So that is literally the Greek letter called alpha. So we're going to use that to represent our types of decay. So all of our different types of decay are using Greek terms to describe them. So an alpha decay is the release of an alpha particle from a nucleus. So for example, we have a radioactive version of uranium. You look at where uranium is on our periodic table. It's at the very, very bottom. It is one of the largest elements. And you will see actually that its atomic number is 92, meaning it has 92 protons. And and let me just really quickly clarify that when I'm writing in this form, I am actually referring to the number of protons goes on the bottom, or its atomic number. And the atomic mass goes on the top. And I know that seems a little counterintuitive because it's reversed on the periodic table, but this is a pretty standard form of writing the number of protons versus the atomic mass for a particular element. So I'll erase that. So again, this element called uranium has a lot of protons. It has a very, very large nucleus. It has 92 protons, and this particular version of uranium, called an isotope, has an atomic mass of 238. Now, it wants to become more stable. At the moment, it is radioactive. It is very high energy. It is ready to become a more stable nucleus. So what it can do is shed what we call an alpha particle. It's going to release an alpha particle. And all that an alpha particle is just an atom of helium. So if you look at helium on the periodic table, you will see that it has an atomic number of 2, meaning it has 2 protons, and it has an atomic mass of 4, meaning that there are 2 more neutrons within that atomic nucleus. So it has 2 protons and 2 neutrons. So this uranium is just shedding 2 protons and 2 neutrons, which we just give the title of as an alpha particle. Now, all of a sudden, it becomes a stable new atom. It has shed 2 protons. So if you look on the periodic table and find the atomic number 90 on the periodic table, that is our atom called thorium. So because it shed 2 protons, it actually becomes a totally different type of atom. It becomes thorium instead of uranium. It also shed 2 neutrons. So it in total has lost 4 universal mass units. So its mass has decreased by 4. It started with a mass of 238 and now it has a mass of 234. So that is an example of an alpha decay. Really what it's doing is it's just shedding 2 protons and 2 neutrons from the nucleus of the atom. We also could have beta decay, say in maybe a smaller atom, because our smaller atoms like to undergo beta decay as opposed to alpha decay because they're losing quite a bit when they undergo alpha decay. So beta decay is releasing a beta particle in a nucleus. So a beta particle could be a positive charge or a negative charge. And I will explain what that means in just a moment. But the ultimate goal of beta decay is that atom is not losing mass. It is simply losing a little bit of charge, and so that a proton in its nucleus could become a neutron, or a neutron in its nucleus could become a proton. It's kind of just readjusting that proton to neutron ratio in the nucleus. So say we had a radioactive lithium atom. You'll notice it has its 3 protons on the bottom here, indicating that it is in fact lithium, but it is an extra large atomic mass. It is ready to shed some neutrons there to become a more stable atom. So what it would do is it's going to shed a beta particle. And this is actually our pretty standard notation for beta particles, indicating that it is going to lose a little bit of that negative charge here. And as a result of losing its negative charge, it's going to gain a little bit more positively charged subatomic particles. So it goes actually from 3 protons, it loses some negative charge, and it results in it having 4 protons. So when it has 4 protons, it now becomes a new atom. It is now beryllium instead of lithium. But beryllium with 4 protons and 4 neutrons is a very stable atom. So it really hasn't lost any mass at all. What it is, see how it's still the same mass up top, but what it's really done is it's just taken one of its neutrons in the nucleus and just shed a little bit of that negative charge from that neutron to become overall a positively charged proton. So that's a really cool process as well that atoms can undergo, called beta decay. Again, ultimate goal is not to lose mass. It is simply to convert one of its protons into a neutron or one of its neutrons into a proton. Now, the last type of decay we could see is something called gamma decay. And that is the release of a gamma particle from the nucleus. Again, I'm not going to quiz you all on all the nuances with these different types of decay. But what I want you all to understand is that gamma particle, and this is our symbol for gamma. It looks like an upside down alpha symbol, is simply a photon. So if we have this atom of barium, it's got an atomic number of 56, meaning it has 56 protons. Its atomic mass is 137. If it releases some of its energy, again, it's not losing any mass, it's just releasing some energy, all right, in the form of a photon, it would become more stable. Again, notice how the number of protons didn't change. It's still a barium atom, and the number of particles, aka its mass, did not change. It just lost a photon to go from radioactive to a stable isotope of barium. So understanding these processes in fission and fusion and radioactivity allows us to actually perform some calculations. It leads us to this understanding of what is called the mass energy equivalence. And I will highlight that for you all because this is an important term. Which is a little bit of a difficult concept to grasp. But what I want you all to recall is that we've learned two different laws of conservation. We've learned the law of conservation of mass, which states that mass can neither be created nor destroyed. All the mass in our universe is a finite amount. We cannot create more mass, nor can we destroy mass. And the same thing with the law of conservation of energy. We know that the law of conservation of energy states that energy can neither be created nor destroyed. It can only be transferred between forms. So this idea of mass energy equivalence states that mass can be converted to energy, and energy can be converted into mass, basically. And that gives us a famous equation, if you recall, E equals mc squared. Which allows us to perform a lot of our nuclear physics calculations. So this says that the energy of an atom or some other object is equal to the mass of the atom or a portion of the atom times the speed of light squared. So we will run through how we can calculate, use this equation in an example problem in just a moment. But do note that this is a very, very famous equation. This is a bit of a difficult concept to grasp because it can be pretty abstract, but really, thankfully, it is a simple equation in terms of the math that we will be doing. So that brings us to our example problem here. And I will zoom in a little bit. All right, so this problem says the mass of an oxygen atom's nucleus is 15.99 U, or atomic mass units. What is the atom's binding energy? And I did include the conversion, which says that 1 atomic mass unit, or 1 U, is equal to 1.7 times 10 to the negative 27th kilograms. So the very first thing that I've done is I've drawn our oxygen atom in step number 1. And I have also written out its mass in atomic mass units, which is 15.99 U. So for the sake of math and for simplicity, let's go ahead and convert this number into our standard unit of measurement, which is in kilograms. So to convert 15.99 U into kilograms, we are simply going to multiply 15.99 times 1.7 times 10 to the negative 27th. And again, just make sure that you all are keeping track of those units of measurement and keeping track of those parentheses. And you all should get something that is close to 2.7 times 10 to the negative 26th power in kilograms. All right, so we can actually rewrite our mass. I'll do this in a different color here. As 2.7 times 10 to the negative 26 kilograms. I'll go ahead and do that. So again, that is one of our known values. Another thing that we do know is the speed of light. If you recall, the speed of light is always going to be the same number. That lowercase c is going to be 3.0 times 10 to the 8th. I'm going to rewrite that. Meters per second. We always know what that number is going to be. Now, the last thing we need to figure out is what we are solving for. So this problem asks at the end, what is the atom's binding energy? So if we recall from the beginning of this video, our definition of the binding energy is the amount of energy required to overcome the strong force that holds the nucleons together in the nucleus. So what it's really asking, this problem is asking how much energy is required to break up the nucleus of this oxygen atom and break up those protons and neutrons. So but energy is energy, so we know that we are solving for energy here. All right, so now that we've got everything laid out, we can go ahead and move on to our step number 3, which is getting our equation set up. E equals mc squared. All right, thankfully this is all set up to solve for our unknown value, which is E. So we can go ahead and start plugging those numbers in. Remember, we are plugging in our mass value, which is 2.7 times 10 to the negative 26 power in kilograms, being multiplied by 3 times 10 to the 8th meters per second. And that is all going to be squared. All right, so go ahead and take a moment to plug this in your calculator and compare that to what I get. And y'all should get an answer that is about 2 times 10 to the negative 9th power in joules. You could also think of it as this many joules in standard notation. So that is our binding energy. That is the number, the amount of joules required to break apart the nucleus of an oxygen atom. So again, hopefully that gives you all a pretty good overview of many topics related to nuclear physics. I know that that was a lot of information in this video. But again, please don't forget to write a 1 to 2 sentence summary about what you learned from the video. And I look forward to discussing this with you all more in class.